The last type of titration that we're going to look at in this topic is using a titration to determine the degree of hydration in a hydrated salt. In this video, we're going to look at the theory behind the titration and a few examples of the calculations, and then in our next lesson we'll have a look at an example of one of the whole practicals. So hopefully you remember from GCSE that a hydrated salt is one that contains water of crystallization. A common example that was looked at was hydrated copper sulfate, and you can see this formula has three parts to it. We have the part of our salt, CuSO4, and if I was to take away the dot and the 5H2O, we would call that an anhydrous salt, in other words, one without water. This dot means that the salt is bonded to water molecules. So those 5 water molecules are actually bonded to the copper sulfate molecule. I've just drawn a very rough diagram there or picture of that, that the copper sulfate is actually bonded to 5 water molecules. I haven't drawn it in any particular shape or anything like that, but it's surrounded by water, but it's actually bonded to the water molecules. So we were saying we have 3 parts to this formula. The anhydrous salt is such, if it was on its own, the dot representing that the salt and the water molecules are bonded together, and then you've got the waters themselves. Within this formula, we know that we have 5 water molecules. We have 5 molecules of water of crystallization, but sometimes we don't know how many water molecules there are, and that's what we're using this titration for, to determine the degree of hydration. In other words, to determine what is this number, how many water molecules are there bonded to each of my molecules of my salt. And you've done a similar type of calculation before. You have already learned a method of determining the degree of hydration. I wonder if you remember back to your formula and equations and calculations topic at the start of Unit 1. You learnt that you can determine the degree of hydration by heating a hydrated salt to constant mass. In other words, heating it so that the water molecules evaporate. If you do that, you would have measured your initial mass of your hydrated salt. Once you heat to constant mass, you will know the mass of your anhydrous salt, and therefore you will be able to work out the difference between the two will be the mass of water that has evaporated. What you can do with that then is work out the number of moles you have of your anhydrous salt and your water, and then use a ratio to calculate your number of water molecules. What we are going to be looking at in this topic is a slightly different method of determining the degree of hydration, but that final step will be very similar. We will be weighing out a known mass of our hydrated salt, so we will know the mass of it. And then what we're going to do is dissolve it, make up a standard solution, or a solution of known volume anyway. And then we will take that mixture, that solution, and we will titrate it against something else. And when we dissolve a hydrated salt in water, the water molecules break off just like they do when we heat them. So when it's dissolved in water, that bond, that water of crystallization bond gets taken away. And so we have essentially our anhydrous salt dissolved in water, just mixed with it, no longer bonded. And so what we can do is then take essentially our anhydrous salt. When it's dissolved in solution, it reacts just as the anhydrous salt. We can titrate it. And when we titrate it, we will be able to work out the number of moles of our essentially anhydrous salt. Once we know our number of moles of our anhydrous salt essentially within our solution that we've made up, then we can go and work out the mass of the anhydrous salt. And then we can work out the mass of water by taking away the mass of my anhydrous salt from my hydrated salt. Once I've got the mass of my anhydrous salt and my mass of water, then again calculate the number of moles of each of those. And just like you did before earlier on in Unit 1, we get the degree of hydration by doing a mole ratio of each of those. So let's have a look at page 40 to see if we can get our head around these. That was quite an abstract example. And in fact, you wouldn't use a salt like copper sulfate because that is not able to be titrated against anything. Quite often the example used is hydrated sodium carbonate, and that's essentially washing soda crystals. So sodium carbonate has the formula Na2CO3, that's sodium carbonate, but when it's hydrated, we write its formula as Na2CO3.XH2O. So that means it's bonded to a certain amount of water molecules, and our aim is to calculate how many water molecules it is bonded with in the initial hydrated salt. In other words, determining the value of X in your salt.XH2O, in other words, the degree of hydration. So looking at the second paragraph here, when a hydrated salt is dissolved in water in a beaker and the volume is made up to 250 centimetres cubed or any other known volume, the mass of solid being dissolved also includes the mass of the water of crystallisation. So when you weigh out that hydrated salt, obviously the mass of the solid includes the mass of water of crystallisation. But when it's in solution, as we mentioned before, the water of crystallisation is no longer a factor, because essentially those water molecules break away and they are just mixed together. So you have your essentially anhydrous salt mixed in with water molecules no longer bonded to them. And that's represented in the equation that you can see. The little arrowhead is missing, so you could add that in. Just here. So our hydrated sodium carbonate would break up into sodium carbonate that we can essentially treat as anhydrous, but obviously it is dissolved in water, but it's no longer bonded to the water, plus your XH2O. Sodium carbonate solution is a base, and so we can then titrate that solution against an acid. We will want our acid to have a known concentration. It will be our standard solution, so it will go in the burette. And the solution of sodium carbonate or whatever other salt I've used will go into the conical flasks. And as we've mentioned before, during this titration, the reaction of the solution of the sodium carbonate or whatever other salt that you've used with that titration with the acid occurs as if the salt were anhydrous, for example, sodium carbonate on its own. So if we were titrating it against hydrochloric acid, this would be the equation for your reaction. And this equation of the reaction follows the general equation: metal carbonate plus acid gives salt plus carbon dioxide plus water. And it is important that you can write the equations for these titration reactions. As we've seen, it affects the balancing number ratio, which affects our whole moles calculation. So the aim of the titration is to determine the number of moles of our anhydrous salt as such, the one that's dissolved in the water. Because essentially what will happen is we'll know the titer of our hydrochloric acid, and so we'll be able to work out the number of moles of this. So the moles calculation will start here as always, and then we will be able to calculate the number of moles of our sodium carbonate based on our ratio. It's 2 to 1 here, so we would have to divide by 2. You don't necessarily need to add all of this in, by the way. Once we have our number of moles of sodium carbonate, we can determine the mass simply by using the equation mass equals N times RFM. Once we've got the mass of our anhydrous salt, then we can work out the mass of water that we have within our original sample, because we will know our mass of hydrated salt that we measured out at the start. Then we can take away the mass of the anhydrous salt, which we've just determined from our titration. And the difference between those two masses is going to be the mass of water. As the final paragraph says, then we want to calculate the moles of the anhydrous salt and the moles of water of crystallization, and that gives us a simple ratio. We calculate the number of moles by doing N equals mass over RFM. And we put those in a simple ratio to each other. The moles of the anhydrous, so our Na2CO3 in this example, to our number of moles of water. And when we work that out in its simplest integer form, then that will give us the number of moles of water and the number of molecules of water in our hydrated salt. In other words, the value of X. So at this stage, it's very similar to your calculations that you would have done earlier on in Unit 1. But just how we determine the mass is slightly different. We're determining the mass of the anhydrous salt by dissolving it, forming a solution of it, and then titrating it. Whereas previously you would have heated to constant mass to determine the mass of your anhydrous salt. But this ratio stage is exactly the same. So this is an overview of the method and a diagram to represent that, and essentially then how we get our different calculations from this. Again, I would recommend drawing a diagram like this when you're doing calculations, even if you're not doing it in a practical sense, because it sometimes helps us get our head around the practical and therefore working backwards essentially from our moles calculations. So we start initially with our known mass of our hydrated sodium. That should say sodium carbonate. I think that's just been cut off by one of the text boxes. So when you're doing this, and this must be done so accurately, and we'll kind of cover that in our practical video in our next lesson, but you've got to know the mass exactly, because if you don't know the mass that you initially put into the solution, then you can't know for sure what the mass of water is when you take away the mass of the anhydrous. So it's so important that you know the mass of your hydrated salt accurately at the start. You dissolve that in water, get it to dissolve first of all, and then you place it into a volumetric flask, because in a volumetric flask you can make it up to a certain volume and know that exactly. The next step will be taking a sample from the diluted solution and adding your indicator, so you'll be placing that in a conical flask. And this is where we need to think about our number of moles of our sodium carbonate. Okay, so if we go back to the start with our solid, we're putting that all into the beaker and dissolving it in water. We're then putting that all into the volumetric flask. But then when we take our sample out of the volumetric flask, we're only taking 25 out of 250 centimeters cubed of our solution. Therefore, I'm only taking 1/10 of the moles of my sodium carbonate. So that's where we need to be careful with our calculations. Because I'm only taking 25 centimeter cube sample, this conical flask only contains 1/10 of the moles of my sodium carbonate. So up to the point of the volumetric flask, all of the moles are transferred in from your solid sample into the beaker, then into the volumetric flask, and we do lots of rinsing to make sure all of that goes in. But then when you take the sample for the conical flask, you're only really titrating 1/10 of it, and we've got to factor that in when we're working backwards for our moles. Another little small mistake to change in your notes, and this is just an example. The concentration of the hydrochloric acid could be different. It could be sulfuric acid or nitric acid that you use, but this is just a particular example. Similarly, the volume of your volumetric flask might be different, but you're just taking into consideration the proportion of the sample that you take. So that should say hydrochloric acid in the burette. I think this was just maybe copied from one of the previous similar diagrams. If you could change that to hydrochloric acid. So we know the concentration of our hydrochloric acid, so that's our standard solution. So once we've got our titer, we can work out the moles of hydrochloric acid. So we do that using N equals CV. The concentration we know, and the volume is essentially your average titer. So that's where our moles calculations start, and that's where these backward arrows come into play. Just to say, we tend to use methyl orange in this type of titration. Sodium carbonate, it's a funny one. It's not necessarily stated as a weak or strong base. It's not as weak as ammonia or anything like that, but in some senses it's considered a weak base. So we tend to use methyl orange. Colour change at the end, it says yellow to orange here. Generally, we code it as the two extreme colours, so from yellow to red. So it can be yellow to orange or yellow to red is the colour change we're looking out for. But where it says number 1 here, that's where our calculation starts. Our calculation starts here because we have two values for hydrochloric acid. We have our titer for our volume, we have our concentration, so we can work out the number of moles. Then we can transfer that to work out how many moles of sodium carbonate there was in the conical flask. How do we do that? Well, we do that by our reaction equation. And I've written that at the top, although it's on the previous page as well. So that's the equation for our titration. So once we have our number of moles of hydrochloric acid, we can bring that across to the sodium carbonate. But have a look at the ratio, it's 2 to 1. So what we want to do is we want to divide our number of moles of hydrochloric acid by 2. Again, it might be a different acid and the ratio might be 1 to 1, it might be a different salt. But in this example, you're dividing your number of moles by 2. So if you want to write in there, dividing by 2, and that's because your ratio is 2 to 1. Okay, so that gives us our number of moles of sodium carbonate in our conical flask in 25 centimetres cubed. But then moving backwards, we then want to work out the number of moles in our volumetric flask, and that's in 250 centimetres cubed. Remember when we were going this way, we said that we're taking 1/10 of the moles from our volumetric flask into the conical flask, which means when we're working backwards, we have 10 times as many moles in the volumetric flask as we do in the conical flask. So here, we are multiplying by 10. Sorry, I'm choosing the wrong type of pen. So when you're moving your moles from the conical flask to the volumetric flask, you're timesing by 10 because you only took 1/10 of the sample from the volumetric flask into the conical flask. But be careful to read the question carefully, because you might have just made up 100 centimetres cubed of your solution, in which case it would be multiplied by 4 at this stage, because you would be taking 1/4 of the moles out. So that's why it's helpful to think of this diagram, because you are thinking about it towards the titration, and then the moles you're working backwards. Then we want to use the number of moles of sodium carbonate in our volumetric flask to work out the number of moles of sodium carbonate in our initial salt. And that is exactly the same. We don't need to do anything. You can say, I sometimes say times by 1. Why is that? It's because we transferred all of our salt into the beaker to be dissolved, and then all of that into the volumetric flask. So that volumetric flask contains all of the moles of sodium carbonate that we started with in our initially weighed out sample, our known mass of the hydrated salt. So moving backwards then, the number of moles of sodium carbonate in the volumetric flask is the same as the number of moles in the initial sample. So once we are at step number 4 here, then we know our number of moles of sodium carbonate in the mass weighed out. So from that, we can work out the mass of essentially the anhydrous salt that we would have had. We do that by using the equation mass equals N times RFM. That gives us the mass of our sodium carbonate, essentially the anhydrous. Because remember, when we dissolve it in a solution and when we titrate it, it's reacting as if it was the anhydrous. The water of crystallization that was initially there will have broken off and is not part of that salt at that stage. So what you'll find is that mass of the anhydrous sodium carbonate should be less than your initial mass that you weighed out. Why? Because the initial mass was your hydrated salt. And so from that you can work out the mass of your water by doing hydrated minus anhydrous. So your mass of water is the difference between the mass of your hydrated salt, take away the mass of your anhydrous salt, which we've determined from the titration. So I've just written underneath that the hydrated salt, and that's your initial mass of the salt you weighed out. The anhydrous, I've just put a wee star back to step number 5. That's the anhydrous mass that you worked out in the previous step. From the mass of your water, we're nearly there. From the mass of your water, you can then, you can then work out your number of moles of water, and from that you can work out your value of X. How you do that is you put those in a simple ratio against each other, moles of your sodium carbonate to the moles of water, and work out what your ratio is in an integer form, and that gives you your value of X. So at that stage, as I said, that's very similar to the ones that you did back earlier on in the unit. So I know we've taken a good bit of time to go through this, and hopefully that was helpful. I know some of you were finding the dilution titration calculations quite hard, but you can see this is very, very similar. It's the same initial steps, but then that last step goes a wee bit further in terms of determining that ratio. But hopefully that's helpful in letting you see how you work backwards to get your number of moles in the initial sample. And it's all about thinking about your practical and what you've transferred to what portion you've brought out, and therefore working backwards. How does that affect the number of moles of your solution in each piece of apparatus? So that's why I think it's really helpful to draw a diagram like this in your calculation, because then you have a better understanding of your practical, and then you will be able to do the steps of your calculation a little bit better and understand what they are asking you for, the number of moles at which stage. Page 42 just talks about how to prepare a solution in a volumetric flask of a solid. And this just, remember, a volumetric flask gives you a really accurately known volume. And that's important for our titrations, because we need to know that, say for example, this volumetric flask contains exactly 250 centimetres cubed. So if I'm pipetting 25 centimetres cubed out for my titration, that I know that that sample contains exactly 1/10 of the number of moles. This method is really important, and it's important that you learn this method. I will take you through it in the practical video when I show you making up a solution using a solid. It's quite similar to making up a solution from, just a dilution, but there's a few extra steps when you start with a solid. First of all, you must weigh out accurately whatever mass of your solid in a weighing boat. You really need to know the mass, because otherwise you can't work out essentially your concentration of that solution or how much of your salt you initially added in. Then what you want to do is you want to put that into a clean, dry beaker. Again, I'll take you through this again in the practical video. You want to then rinse your weighing boat with deionized water and put that into the beaker. Why is that? Well, if I know the mass of the salt that I've weighed out in the weighing boat, I want all of that to ultimately end up in my volumetric flask. So if it's been transferred to the beaker, I want to make sure that all of the salt goes from the weighing boat into the beaker. And then what you want to do is add approximately 100 centimetres cubed of water. You don't want to add the full 250 because you want to make that up accurately. So you put approximately 100 centimetres cubed of water. That should be enough to get your crystals to dissolve. You stir using a glass rod, but you don't remove the glass rod at any point during the process, because again, the glass rod will have some of the sample on it. It will have some of your solution which contains some of your dissolved salt, and you want it to get all from your initially weighed out sample into the volumetric flask. So as you remove the glass rod, you want to rinse the glass rod with deionized water. Basically anything that the solution or the original solid touched, you've got to rinse with deionized water to make sure it all goes in. Because if I leave some behind, then I no longer know the mass of the salt that's in my solution. You then transfer into a volumetric flask using a glass filter funnel, which means my solution is now touching that, so that's something else we have to rinse. But before that, we've transferred it from the beaker, so we've got to rinse the beaker with deionized water and put that into the volumetric flask. Quite often this is referred to as, add from the beaker with washings. And then you finally rinse the filter funnel because it's got a little bit of the solution. So anything that's got a bit of the solution or the original solid, you've got to rinse it and make sure all of that goes into the volumetric flask. You make up the solution very carefully to the 250 centimetre cube mark until the water level, the bottom of the meniscus is on that mark. Again, that's got to be done so carefully, because if you overshoot, if you go a little bit over, you have to actually start again, because you can't just remove a little bit to get it back down on the mark, because that little bit that you remove will contain a little bit of your dissolved salt. So you cannot do that. So you've got to make it up, adding dropwise towards the end to get it right on that mark. Then you know it's exactly 250 centimetres cubed. What you want to do is insert the stopper, that's important, and then you invert it several times and shake to thoroughly mix it so that you know it's all dissolved and you know it's all evenly distributed. So that when you take a sample out, you know that it contains, say for example, exactly 1/10 of your dissolved salt. So over on page 43, we have a worked example of one of these types of calculations. We'll get our head around the calculation and then in our next lesson we'll have a look at the overall practical. I'll demonstrate that for you and we'll do a calculation based off that real life practical. So I'm going to do this by drawing my my diagram for this, and I'll highlight the important information as we go. So we start with a 3.432 gram sample of our hydrated salt, and there's the formula there, Na2CO3.NH2O. The symbol in front of the water molecules, it doesn't matter, it's just representing the number of water molecules. So the solution is transferred to a 250 centimetre cube volumetric flask and made up to 250 centimetres cubed using deionised water. You can highlight that as well, but that's part of the same part of the method. Then we take a 25 centimetre cubed sample. That's again important. And we pipette that into a conical flask, and our indicator is methyl orange. The question sometimes asks about your colour change, so make sure you know that for your methyl orange and your phenolphthalein. The solution is titrated against 0.1 molar hydrochloric acid. That's our concentration of hydrochloric acid. And we have our results in the table below. So you have your rough, your first and your second titer. Now, this question has not been broken up into individual steps, and so we will just be doing it as a whole calculation. Quite often, especially at this stage, they are given to you in broken up steps. But what we will need to know from our practical results is our average titer. So we'll work that out now. So you can see your titer, and we ignore the rough. And we take our average from our two accurate titrations. So you can see that your average titer is just 24.0 centimetres cubed. If you want to, you can do 24 plus 24 divided by 2, but that's going to give you 24.0 centimetres cubed. Remember, in your calculations, you must convert this into decimetres cubed. You do that by dividing by 1,000. And that should give you 0.024 decimetres cubed. And sometimes it's worthwhile doing that at the start in case you forget in the midst of the calculation. So let's draw a diagram to represent this reaction. So we'll keep it similar to the diagram as we drew for our dilution calculations. So we're starting with 3.432 grams of our sodium carbonate, our hydrated sodium carbonate. And we just weigh that out in, well, a weighing boat, and then we dissolve it up in a beaker. But I've just drawn it in a beaker. It doesn't really matter what you draw it in at this stage. And writing down your mass will help you with your calculation as well. So we're told that that is dissolved in water and then all transferred. The solution is transferred into a volumetric flask and made up to 250 centimetres cubed. So we can draw that as being transferred into a volumetric flask. Sorry, my drawings are not excellent. And that's made up to 250 centimetres cubed. So that's our sodium carbonate solution. We no longer refer to it as hydrated because remember, those water molecules will have broken off and just been mixed in with the solution. What we do need to remember though is that we transferred all of our original sample into the volumetric flask. So that means all the moles of my sodium carbonate are now in the volumetric flask. So let's read on with our method. We're then told a 25 centimetre cube sample of this solution is pipetted into a conical flask. So what we've done is we've taken 25 out of 250 centimetres cubed and put it in our conical flask. So I write that on the arrow to represent that that's the portion I've taken out. So what portion am I taking out from my volumetric flask? Well, I'm taking out 1/10 of it. And that's in my conical flask. You can see in red I've written underneath the apparatus that I'm in, just because often the steps in the questions will say how many moles are there in the conical flask, in the sample in the conical flask, and you're thinking, oh, well, what stage is that at? And this will help you with that. So you can see that I've got 1/10 of my sodium carbonate solution in the conical flask. What do we then do with that? Well, we add our indicator and then we titrate it against our hydrochloric acid. I normally draw that out separately because this is a separate part of the calculation. I'm just going to scroll this across for now so that we have a wee bit more room. So in our burette, we're told that we have our 0.1 molar hydrochloric acid. Remember, molar is just another unit for concentration in moles per decimetre cubed. And we know that our volume of this, as we worked out from our average titer, is 0.024 decimetres cubed. I'll need both of those to work out my number of moles of HCl by using the equation N equals CV. And then from there, I'll be able to work out my number of moles of sodium carbonate based on my reaction equation. So if you haven't already been asked to do so, it's a good idea to write your balance symbol equation for the reaction in order to get your balancing number ratio. So I'll write that at the top. So we've got sodium carbonate, Na2CO3 plus HCl. Remember, we're going to get a salt, water and carbon dioxide because this is a metal carbonate reacting with acid. So our salt is going to be sodium chloride, which has the formula NaCl, because each of sodium and chlorine have a valency of 1. We have water, H2O and CO2. We need to balance that equation, and we can see to balance it I've got 2 sodiums in the left but only 1 on the right, so I need to put a 2 in front of my NaCl. And then that affects my chlorines, so I need to put a 2 in front of my HCl, and that also balances my hydrogens, and you can see your oxygens and carbons are already balanced. So that's our balance symbol equation. So we can see, if I write this down here again, just the left hand side of the equation we are concerned with, but I do need to write the whole equation in order to get it balanced. Okay, so we can just write the first half of it. We're going to start with our number of moles here, and we're going to bring it over to our number of moles of sodium carbonate in our conical flask. That ratio you can see is 2 to 1, so I'm going to be dividing my number of moles of hydrochloric acid by 2. So what I like to do at this stage, just to make sure I've got an idea of what's happening in terms of the moles, is I kind of work my arrows backwards. So from that, I've been able to work out how many moles of sodium carbonate I have in the conical flask. So to represent that stage in terms of essentially the titration, I do that as my first arrow backwards. Essentially from my titration, I know that on my conical flask, the sample of sodium carbonate, the number of moles is divided by 2. Why is that? It's because I have a 2 to 1 ratio. Sorry, that's quite squeezed in, but divided by 2 because you've got a 2 to 1 ratio. Then if we're moving from our conical flask back to our volumetric flask, well, what we need to remember is that we took out a 25 out of 250 centimetre cube sample. That means our conical flask contains only 1/10 of what's in our volumetric flask. So working backwards, I'm timesing my number of moles by 10. Okay, so that's times 10. If you want to write the word moles to remind yourself that that's what these blue arrows represent. So there will be 10 times as many moles of sodium carbonate in my volumetric flask as there are in the conical flask, which was used in titration. And then if I want to work out how many moles of sodium carbonate there are in my original sample, well, because I transferred all of it from the original sample into the volumetric flask, then it's the same. Even though I've diluted it, yes, that's affected the concentration, but it hasn't affected the number of moles. So dilution does not affect the number of moles. Now, sometimes you're told that you pipette a certain portion of the sample into the volumetric flask. That's when you need to think about the number of moles, but hopefully at this stage they wouldn't give you that. But we know from this question anyway that all of the sample was transferred into the volumetric flask, so it contains the same number of moles as the original sample. So at that stage, it's just times by 1 essentially. In other words, it's the same number of moles. So from this point, we are ready to do our calculation. And I'm just going to scroll up so that I have plenty of room to write my calculation. What I'll do is I'll write it underneath the balance symbol equation because that's essentially where we start. But as I said, often these are broken up into individual parts of the question. So we're going to start with our number of moles of hydrochloric acid because that's what was in our burette. Essentially, all titration calculations start with the titer and whatever was in the burette. So the first part of the question, if this was broken up, it would quite often say how many moles of hydrochloric acid were used. So we're doing N equals CV, our concentration is 0.1, our volume is our average titer, which is 0.024 decimeters cubed. Remember, because our concentration is in moles per decimeter cubed, our volume must be in decimeters cubed. That gets you 2.4 times 10 to the minus 3 moles, or you can write it as 0.0024 moles. Okay, the next part of the question would likely be, how many moles of sodium carbonate are there in the conical flask? Well, that's this stage here, where you are working out how many moles did you have in the conical flask for reacting in the titration. And that's where we bring in our balancing number ratio. We can see our balancing number ratio is 2 to 1. So we're dividing the number of moles of hydrochloric acid by 2, technically timesing by 1. And that is going to give us 1.2 times 10 to the minus 3 moles. And that is, if you want to maybe write in red, that's in your 25 centimetre cubed sample in the conical flask. So even if you write CF in the conical flask. So I know I have 1.2 times 10 to the minus 3 moles in the conical flask. At that point, you could work out your concentration, but here we're more interested in moles because we're then going to convert to mass. Okay, so if we're then moving into the volumetric flask, so with the volumetric flask, we're going from a 25 centimetre cube sample to the whole 250 centimetre cube sample. We are at this stage of the moles calculation, so we need to multiply that number of moles by 10. I have 10 times as many moles in my volumetric flask as I did in my conical flask. So in order to work out how many moles I have in the volumetric flask, I take my 1.2 times 10 to the minus 3 that I know I have in my conical flask. I times it by 10, and that gives me 0.012, or in other words, 1.2 times 10 to the minus 2 moles. So I know I have 0.012 moles in my volumetric flask. So then we're really thinking, how many moles of sodium carbonate do I have in my original solution, or my original sample? That's this stage of the moles calculation. So really it is the same. That is the same as the number of moles in the original sample, because we transferred it all into the volumetric flask. So I know this is a bit all over the show, but normally there would be structured steps for you to follow. But that means I have 0.012 moles in my original sample. What is that the number of moles of? That's the number of moles of Na2CO3, essentially your anhydrous Na2CO3. So that's the number of moles of sodium carbonate that we have in our original sample minus the water, essentially. So that's our titration part of the calculation over as such, so we can move that out of the way. And what we then want to do, and if you look back at the previous page, if you're not sure what to do at this stage, but the rest of the questions we'll do will be structured, so they'll guide you as what to do next. What we want is essentially the mass of the anhydrous sodium carbonate, and from that we'll be able to work out the mass of water. So in order to work out the mass, I'm using the equation mass equals N times RFM. My number of moles is 0.012, which I've just worked out from my titration. And the RFM of sodium carbonate you can work out is 106. Put that into your calculator and you get 1.272 grams. So that's the mass of the anhydrous salt within your hydrated salt. What I then need to work out is my mass of water, because remember my ultimate goal is to do my ratio of moles of anhydrous to moles of water, just as you would have done in your previous way of working out degree of hydration earlier on in Unit 1. So in order to work out the mass of water, I need to get the mass of my hydrated salt, which is given to me in the question, and I take away the mass of my anhydrous salt, because the difference between the two is going to be the mass of water of crystallization within the hydrated salt. So you're told in the question, go back to the start of the question, you're told that the hydrated salt, we measure out 3.432 grams. And the mass of our anhydrous salt is 1.272 grams. So that gives us a mass of water of 2.16 grams. What I can then do is work out my number of moles of anhydrous sodium carbonate, my number of moles of water, and put them in a ratio together to get my number of water of crystallization. So this step is really important. Sometimes people just put the two masses in ratio to each other, but that is not correct. You can only put the mole ratio together, because within your formula of the hydrated salt, it's how many moles of the salt is there to how many moles of water. So you need to remember to convert to moles at this stage. You would have done this in your degree of hydration calculations before. So our number of moles of our sodium carbonate, well, we know that the anhydrous mass is 1.272 divided by our RFM, which is 106, and we know that that gives us 0.012. It's essentially the reverse of this calculation here, up above. With our water then, our mass is 2.160 divided by the RFM of water, which is 18. And that gives us 0.12 moles. And then what we want to do is get this in the simplest ratio. How we do that is we divide by the smaller number of moles. So hopefully that's familiar from doing these types of calculations before. Divide by the smaller number of moles, but please write that down if you can't remember that. In this case, that's our sodium carbonate, 0.012. So we divide both of those numbers by 0.012. That's going to give us 1 mole, obviously, of our sodium carbonate. And then 0.12 divided by 0.012 gives us 10. So that means for every 1 mole of sodium carbonate, we have 10 moles of water. So that is our degree of hydration. So the formula of our hydrated salt is Na2CO3.10H2O. In terms of determining N is equal to 10. We have 10 waters of crystallization. So what I want you to do for now is to skip the practical. I'm going to demonstrate that to you in our lesson next week. So you can skip past pages 44, 45 and 46 and turn to page 47. And what I'd like you to do is to try exercise 8. So there are just 2 questions, question 1 and question 2. Give these a go. They are very similar to the ones we have just done before. They are using sodium carbonate for both of them, but just be wary. The first one is with hydrochloric acid with the titration. Second one is with sulfuric acid, so make sure you write the correct balance symbol equation for that reaction. But these are broken up into steps, so hopefully that you will find that a bit easier. I would encourage you to draw a diagram to help you make sense of that, if you find that helpful, and just help you keep a track of the moles and what they're asking for at each stage. So draw your diagram, think about what portion you're taking out at each stage, and then track back with your moles. So if you complete those 2 questions and submit them to the assignment on Teams, just so I can see how you're getting on with those and do you need some extra help with those. And if you can submit them as a Word document, that would be great. It just means I can write over them and attach your work to the assignment on Teams and feed that back to you. But as always, if you're struggling with these, if you're not sure where to go next with the calculations, or you get stuck partway through, please do just get in touch.